All right, let's talk about inverse matrices. We've seen these before, but it doesn't hurt to go over them again. Square matrix M is invertible if there's another matrix which we call M inverse, so that if we multiply M on the left or on the right by M inverse, we still get the identity. So here we're saying invertible, or we can say non-singular. All right, so there are many definitions of non-singular. In this section, we're going to use the definition that a matrix is non-singular if and only if it's invertible. In the 2 by 2 case, there's a formula for the inverse. If AD minus BC is not 0, then we can define this matrix here, and that turns out to satisfy this inverse equation for 2 by 2 matrices. Now, for larger matrices, you don't have such a simple formula, but you still can find the inverse. If M has no inverse, we say M is singular or non-invertible. So singular means no inverse. And you can remember singular means unusual. So it's unusual for M not to have an inverse. All right, so here's the formula for inverse of 2 by 2 matrices. And here's some properties of the matrix. It turns out that the inverse of a matrix is the matrix itself. And that's because of the symmetric relationship of the definition of inverse. B is the inverse of A if AB and BA are equal to I. So that's the same thing if A is the inverse of B. All right? So the inverse of the inverse is the matrix itself. Another interesting property is that the inverse of a product is the product of the inverses in reverse order. And there's a proof here. We take B inverse A inverse times AB. The A inverse unpacks the A, and it gives us identity. Then the B inverse unpacks the B, and I get identity. And we could do that multiplying on the left by B inverse A inverse, or multiplying on the right by B inverse A inverse. I still get I, so that proves this property. Okay. Same thing with transpose. We had this relationship before. So you can combine properties of transpose and inverse to show that the inverse of the transpose is the transpose of the inverse. All right. You work through these steps and you find out that that's true. Now this following section is basically a review. We saw somewhat earlier in chapter 2 that the way to get a matrix inverse is to take the matrix M and augment it by the matrix I, and then row reduce. Now we know that if you have an invertible matrix, then the solution to mx equals v is x equals m inverse v. So the Gaussian process can be represented in this way. If I take the m and I augment it by a vector v, then I row reduce. Since this is a non-singular matrix, it will row reduce to the identity. And then the v will row reduce to the solution, which is m inverse v. All right. Now, if I have several vectors, I can augment it by more than one vector at the same time and row reduce. And the row reduction essentially multiplies this augmented matrix by m inverse in the case where m is invertible. When m is invertible, that's what happens. We row reduce to the identity, and the row operations amount to multiplying by the inverse of m. So we multiply m by the inverse of m. We're also going to be multiplying the columns here by the inverse of m. Now, what we want to get is m inverse. So what we can do is replace this v1, v2, and so on just by the identity matrix. So what we'll get to the right of the bar is just m inverse times all the columns of the identity matrix, which is the same thing as taking m inverse times the identity matrix. Right. So we've seen this computation before. Really is just kind of a review, but it puts it in context of the current discussion. And on to the next sort section. we have seen that we can take a linear system and express it in matrix vector form. Mx equals 1, 2, 0 in this case, where 1, 2, 0 is the vector of constants. Now, in ordinary algebra, you could solve this by multiplying both sides by an inverse, and we can now, since we have an M inverse, multiply this side by M inverse, multiply this side by M inverse. That gives me x equals M inverse of 1, 2, 0. That's the same principle I was using here when I said that the solution to this equation is x equals M inverse V1. So this just shows you another example of that same principle. So when M inverse exists, you can always find a solution, and in fact M inverse of V will be the only solution to this equation, because I can go from here to here and back the other way uniquely. Any x for which this is true will also satisfy this equation, because I'm just doing the same thing to both sides, just multiplying M inverse by both sides. Okay, recall the definition of a homogeneous system. A system is homogeneous if the vector of constants is 0 here. Now, a square matrix is invertible if and only if the homogeneous system has no non-zero solutions. Okay. Why is that? Because if I take M inverse, I apply M inverse to both sides. If M has an inverse, I apply M inverse to both sides. Here I get M inverse of 0, which is 0. That means x must be 0. So if M is invertible, then it can be shown right away that the solution to this system must be x equals 0. Now, in fact, you can go the other way, that if the only solution of mx equals 0 is x equals 0, then we can, when you row reduce, you actually get the identity, which means that M has an inverse. So here's the result. M is square and invertible if and only if mx equals 0 has only the solution x equals 0. So in other words, mx equals 0 only has the trivial solution. All right, this next section I'll pass over somewhat briefly. In coding theory, you talk about strings of bits like this. The reason you do that is computers understand bits. Every information that's sent to a computer is broken down into bits. So if you're talking about information, you really have to start talking about bits. Now, bits have their own arithmetic. They have their own addition, own multiplication. This is called mod 2 addition, mod 2 multiplication. But you can create matrices of bits, and those are called bit matrices. So basically, a bit matrix is a matrix that only has ones and zeros. So, and these are used in cryptography. So if you're interested, you can read more about that, but I'm not going to say more about that in this video. All right, that's it.